Solving a question, m raised to the power of m plus m raised by the power of m plus another m raised to the power of m equals to 93. And what is going to be the value of m? Of course, we can start from the left hand side, that is the side. I think it will be wise if we can guess what the value of m is likely to be even before we do anything. So we can say if m equals to 1, we adjust. If this is possible, it means we are saying 1 raised by the power of 1 plus 1 raised by the power of 1 plus another 1 raised by the power of 1. The question is this equal to 93? Which is no, because everything here is just 3, then 3 is not equal to 93. So m can never, and it's never 1. What if we say m is equal to 2? Can m equal to 2? Okay, let's replace m with 2 wherever we find m. So we can say 2 raised by the power of 2 plus 2 raised by the power of 2 plus 2 raised by the power of 2. Can this equal to 93? Which is no, because what we are having here, this is 4, this is another 4, this is another 4. So 4 plus 4 plus 4, that's going to give me 12, which is not equal to 93. Then we can guess, let's say if m equals to 3, can it be equal to 93? What we're saying is that we are having 3 raised by the power of 3 plus another 3 raised by the power of 3 plus another 3 raised by the power of 3. Is this equals to 93? That is no, because this is 27 plus another 27, then plus another 27. Adding the whole stuff together, we're going to have 81, and it's not equal to 93. That shows that m can never be 3. So let's guess for the next time, if m equals to 4, what are we going to have? So we are saying is that we're going to have 4 raised by the power of 4 plus another 4 raised by the power of 4 plus another 4 raised by the power of 4. Is this equal to 93? Let's check. It is clearing that this is not going to be 93, because 4 raised to the power of 4, that is 256, another 256, another 256. Adding the 3 together, we're going to have 768, which is not equal to 93. Why are we doing all this? Is to guess what the value of m is likely to be. And as we can see, the value of m is going to be in between 3 and 4, because when we assume that m equals to 3, what we got is 81, which is less than 93. And when we assume that m is equal to 4, what we got is 768, that is above 93. So 81 is the closest to 93, even though less than, and 768 is the next above 93. So we can conclude that whatever the value of m we're going to get, it is sure it's going to be between 3 and 4. So we can put that down here and say m is going to be in between 3 and 4. So if we go astray, this can easily draw our attention to accuracy. Wherever we're going to get is going to be between these two whole numbers. It can be 3 points anything, or all we know is that it's going to be above 3, then it's going to be less than 4. So I haven't achieved that. The next thing we're going to do is to add the left hand side together so that we can reduce the complexity here. I mean this side, if we do m raised to the power of m plus m raised to the power of m plus m raised to the power of m, we can say same thing as 3 m raised to the power of m, then equals to 93. We can divide both sides by 3 now, just to eliminate the coefficient here. So we say this divided by 3, then the other side divided by 3. By so doing, we achieve this 3 cancel this 3. Then we can say 3 goes here 1, then 3 goes here, that's going to be 3, then 3 goes here, that's going to be 1. So at the end of the day, what we have left now is m raised to the power of m equals to 31. So the next thing to do now is to apply natural log to both sides. So we can say we have ln m raised to the power of m equals to ln 31. applying a certain rule of logarithm that says when we have log of a raised to the power of x, this can also be written as x log of a. Doing the same thing to this side, now we're going to have ham ln of ham equals to ln of 31. Now, if we check this left hand side, we can see that we have m here, we have m here, and there is no way we can reduce the appearance of m to be 1. And if it can be easily done that way, we can easily say, okay, m is equal to ln 31. But we need to reduce the appearance of m here exactly to only 1m. If we ever think, okay, let's divide both sides by ln ham, that is to the other side ln ham. Of course, we're going to have this one gone. Then at the end of the day, we're going to have m, which is good. That's what we're looking for, only 1m at the left hand side. But the problem is we're still going to have this ham in the, that is at the other side. So actually the problem hasn't gone because, okay, we still have m here. Of course, we have it here too. That is a clear point that we're not going to divide both sides by ln m. So what we're going to do here is to apply a Lambert W function to both sides of the equation. We must know that if we have a mathematical format of this k exponential of k, applying Lambert function to this format, that is w, which represents Lambert function, this is going to result into k. That is exactly when we have the same thing here and at the same time the same thing as the exponent. So the next thing we're going to do now is to rewrite this m into these formats so that we can apply the Lambert W function. Therefore, this is going to lead us into another exponential identity that says if we have exponential of ln k, this is just the same thing as having k. So as explained earlier on, we're going to rewrite our m in conform to this identity. It should be noted that an exponential of ln m is just the same thing as m, exactly according to this. So the next thing I'm going to do now is to replace my m, the m that is here, as I'm having it here, with this identity. So this is going to replace that. That is, replace my m here. Doing this, I'm going to have exponential ln m, then ln m equals to ln 31. If I wish, I can change this to this position, then return this back to this position. If I do, I have ln m, then exponential ln m equals to ln 31. So at this point, going back to Lambert's W function, especially this left hand side that we've already written, we can see that when we have k exponential of k with Lambert W function, the result is going to be k. That is, if we carry out W function on this, the result is k. Therefore, what we need to observe here is that the ln m that we have here is the same thing as ln m that we have here. Therefore, applying Lambert W function to both sides, we're going to have, okay, Lambert W function to left hand side, which is ln m, then exponential of ln m, that is left hand side, then to the right hand side, apply the same thing, Lambert W function of ln 31. Exactly, we already have the idea what result is going to be here, because it's going to be ln m as it is here. Now we write ln m equals to W function of ln 31. The next thing we're going to do is to remove this natural log from this left hand side. If removed, then we're going to have m is equal to whatever that is at the right hand side here. So what are we going to do to remove this natural log? We're going to apply exponential to both sides of the equation. We're going to have exponential ln m equals to exponential Lambert W function of ln 31. Quickly remember that when we say ln m, we mean, because a natural log, we mean log of m into base e. If you can record that, that is fine, that is great. Then also remember a certain logarithm identity that say if we have a raised to the power of log of b base a, the result is going to be b, because this is going to disappear. This, where am I going is wherever we have here. So it means what we have here is the same thing as exponential of log of m. Then we've already established that link m is same thing as log of m base e, so we have base e here. And according to this identity that we just established here, so this is going to disappear like this. Then what we have left is going to be m. So at the end of the day, according to this illustration, so that shows that this is going to go away. Then what we have here left is going to be m. Now we can boldly say that m equals to exponential of w function of ln 31. By checking the calculator to find what ln 31 is, we have m equals to exponential of w function of 3.433987. Also, by calculator, if we find the w function of this value 3.433987, we're going to have m equals to exponential 1.120208. At the end of the day, when we find the exponential of this value 1.120208, the value of m is going to be m equals to 3.065507. So far so good. This is my final answer. And you might need to remember that from the beginning, we've already established that m is going to be between 3 and 4. We said it's going to be above 3, but it's not going to be up to 4. And that is what we've got in 3.065507. And at the same time, we might need to verify, that is confirm, if this answer is actually correct or not. Since this is my question, all what I need to do is to insert this value of m into each m here and confirm if this left hand side is going to be equal to this right hand side. So if it is, it shows that this value is correct. Therefore, m raised to the power of m equals to 3.065507 raised to the power of the same thing, that is 3.065507. Doing this by calculator, m to the power of m is approximately equal to 31.0. And we can say that m to the power of m plus m to the power of m plus m to the power of m equals to 33. It can be written as 31.0 plus 31.0 plus 31.0, which is equals to 33. That is 93 equals to 93. That shows that this value of m is correct.